This is 2011, step 2, question number 12. It's also question 3 from the step 2 stats support module. It's actually a probability question. So you've got these two people playing a match. Now, the really important thing about this question is that you read through this paragraph super carefully and fully make sure that you understand what's going on. It's pretty clear we need to draw a probability tree. I'm going to do it from Eunice's point of view because it asked me about his point of view here. So from Eunice's point of view, he has a chance of 1 minus p of winning the first game, and therefore p of losing it, because it's just win or lose in each point, I should say. And now in the second and third points, whoever won the previous one has a chance p of winning the next one. So because he won this one, he now has a chance p to win the next one. So when we have a win-lose, it will be p to win, 1 minus p to lose. And conversely down here, because he just lost that game, he now has a 1 minus p chance of winning the next one and a p chance of losing it instead. Now we've got to read more of this, because if we're following this branch, he's now 1, then 1. And if you win 2 games in a row, or 2 points in a row, I should say, then you just win. So that branch ends there. This one has gone win, then lose, so they'll play again. And of course, because he just lost that game, he now has a 1 minus p chance of winning and a p chance of losing via the previous rule. Now, this branch here has gone win, lose, win. And because no 2 points have been consecutive for either player, that's going to be a draw, and the game is played from the start again, exactly as it was before. Here, this has gone win, lose, lose. So that's 2 loses in a row. So Xavier is going to win this point, and we keep going for the rest of it. So he just won that game, so he has a chance P of winning the next one too. This has gone lose, win, win. So he wins. Eunice, I should say, wins that game. And then, of course, this one is lose, win, lose. No one wins. It's a draw. Played from start again. And here he's lost, lost, which means Xavier wins that game because 2 loses in a row. So that's the entire picture setup. All good to go. Let W be the probability Eunice wins and show that W is this thing as long as P isn't 0. So, okay, what we'll do is, if we're looking at this picture here, his chance of winning is obviously P times 1 minus P plus, where's the other branch? This one here, plus P times 1 minus P times P. So that'll make that. Except, that's not the only way Eunice could win, because they could also draw the first game via one of these routes, play the game again, and then Eunice could win that one. Or they could draw twice and start again, and then Eunice could win, or 3 times, and so on. So we've got to factor all of that in, and that's where this division is going to come from, because that's the chance of him winning if he wins in the first match. But if they draw first, which has chance of this times this times this, plus of course this times this times this, if they draw first, then we can say, okay, well, let's times that by the probability of him winning the second game, which is the same as the probability of winning first. So this here is the chance of him winning the first game, or the first match, on the first try. Then this here is the probability of them drawing the first game, which are those 2 branches added together, the 2 draw branches added together, times by the probability of him now winning that replayed game. So it goes draw, then win. Except he could also, of course, draw, then finally win. So we could have 2 lots of this probability, or this probability squared, I should really say, followed by the probability of winning. And that will just continue, because it doesn't say that they ever stop playing. They'll keep playing until there's a winner. So it could go draw, 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 draw. Then finally he wins. They'll just keep playing. So this will sum up forever. And this is where we're going to get the division from, right? Because this is going to be a infinite series that we're going to sum up together. So it's going to be all of these things added together. Thankfully, all of them have this Eunice win probability stuck in them, all of this. So we can factorize that out the whole thing, which is what I've done here. And then it's just going to be 1, because of course this times 1 is itself, plus 1 loss of the draw probability, plus the draw probability squared, plus the draw probability cubed, and so on. And that's going to be the chance of him winning. That's going to be W equals. So we factorized out the chance of him winning on the first try, and then 1 plus the probability of him drawing, plus the probability of him drawing twice, and so on. So this here is just a geometric series, I should say, infinite series. So A is just 1, and R is just this whole object here, which is just being times by it every time. So the sum of this is A over 1 minus R. So this is A is 1 over 1 minus, this is 1 minus all of R. So I've just changed the sign there as well. And yeah, let's just sort this out. I've factorized out some stuff from here, it looks like. Have I? I've just dropped a p squared for reasons that I don't understand. Oh no, sorry, I did factorize out p. There's double brackets in there. I factorized out p from there. And now these 2 things also factorize, because the 1 minus p is in both. So you leave a 1 plus p behind. That's fantastic. This I just expanded out and then sorted out and then cancelled a load of things down. It works out quite beautifully because the 1 cancels with the 1, so you factorize that p out. That'll cancel these two things, and these two things multiply together to make 1 minus p squared. And then, so that goes on the top there, the p's cancel, and if you look there, that makes exactly what they wanted us to get. Show that if p is less than a half, w is bigger than a half, and if p is greater than a half, w is less than a half. So I decided to draw a graph for this. So we're only interested in p between 0 and 1, of course, because it's a probability. If p is 0, you get 1/2 out of this, so we can plot that point. If p is 1, you get 0, because the top is obviously 0. So we get this, and we may as well investigate what happens if p is a half, so I can plug that in as well. And you get, it's 1 minus a quarter, which is 3/4, over 2 minus half, you get a half overall. So that ends up being there. When p is a half, you get w as a half as well. And so then I decided to actually get the sketch out, so look for turning points. So I said w is this. I did some product rule because I can never be bothered with quotient. I can't even remember the formula most of the time. I need to set that equal to 0 to find stationary points. Times everything by 2 minus p squared, and you get this. Expand out, and that has roots via the quadratic formula. Here, root 12 is 2 root 3, so that will cancel a little bit. Now, 2 plus root 3, clearly not relevant, because p can only go up to 1 if it's a probability. So 2 minus root 3, I happen to know root 3 is about 1.7, so I know this is going to be about 0.3, so I can safely put it in here. Maybe I should have done some proper maths to prove that. If you do have to, squaring it out and rearranging will do that job for you. But in any case, I'm going to say it's roughly here, and you have a turning point. And because this graph only has an asymptote at p is 2, which of course is beyond where this graph is even drawn from, this is continuous everywhere else. So it's just going to look like this. And this is what the computer gave me. It just looks like that. And of course, we can just look at this graph now. If p is less than a half, yeah, w is bigger than a half, all the way over. And if, and of course, p not being 0 is helpful because that eliminates that case there. And if p is greater than a half, yeah, w is also less than a half. So fantastic, that all says that. Does w increase whenever p decreases? Well, if p decreases from here, this way, w is also decreasing. So no, it doesn't. And that'll be that done as well. If Xavier wins the match, Eunice gives him £1. If Eunice wins, Xavier gives K. Find the value for which is fair. So we want the amount that Eunice is going to lose to be the same as the amount he's going to gain if they play this over and over again overall. So what we need to think about is Xavier's chance of winning first. Now, we know Eunice's chance of winning is this. This is a win, lose, or draw, except it's not really, because the game can't really be drawn. And the reason for that is that, as we said before, they just keep playing. If it's drawn, they just play again and play again and play again. And because the chance of drawing is somewhere between 0 and 1, the chance of going draw, 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 that's like something between 0 and 1 to the power n, where n is getting really, really big. That's basically 0. So the chance of, so basically this is a win-loss game, right? Because draw, 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 draw has a probability of 0, essentially, forever. So this is either win or lose. So we can just do 1 minus Eunice's probability of winning to find Xavier's probability of winning. We'll collect this together after a bit of work, and we'll eventually get to there. And so from Eunice's point of view, he's going to give away £1 with this probability. So we can just do this times by 1 to find how much he's giving away. And we need to make that the same as the amount that he wins. So that will be K times the chance of him winning. So we want those two things to be the same for this to be fair. It's also told us, I'm going to just obviously expand that out a bit and cancel the 2 minus p's because that's never 0 because p is not 2. And also it tells us p is 2/3 in this case. So we're going to put 2/3 in, and of course this just ends up being some not very difficult maths, and we end up with k is 7/5 to finish up that bit. And finally, what happens when p is 0? So we go all the way back to our probability tree, and we're just going to sub p is 0 into here. So that's just me subbing in p is 0. And then we look at this and we go, okay, well, what's the only thing that can happen here? Well, the only thing that happens is we just do this, this, this. And so it's a drawn. So we go back to the start and it does this, this, this. And actually, I said before that this game is not, it can't be drawn forever. But in this particular case, when p is 0, which before we were saying that it couldn't be, remember? But in the case where p is 0, this is just going to be draws all the time, forever. And no one will ever win. And that's all we have to say. Thanks for watching, and I'll see you next time.